So welcome back friends. So we were looking at the Dirac sea, okay, and we were looking at the introduction of the Dirac solutions, essentially the negative energy solutions. Now it invariantly led to the introduction of the entire picture of antiparticles in a much more concrete fashion. The introduction of Dirac sea, that is the reason why now, and it also has applications in condensed matter physics. So that is the reason why we are revising it essentially. Okay. Now, so what is happening in the Dirac sea? So Dirac used Pauli exclusion principle and said that all the negative energy states of the Dirac the negative energy states in a system which are sort of discrete or something, or in a quantum mechanical system, are completely filled up. All the negative energy states, which are nothing but negative energy wave functions, are completely filled up. So there cannot be any more transitions. So this is the way. So we had this puzzle essentially, why cannot atomic transitions happen, and these, because if they are all completely filled up, you cannot put the electron here essentially, you can, if they are completely filled up. So he filled them all up essentially that, and he called it as a vacuum essentially. All the negative energy states are completely filled up, so you cannot have any more transitions, otherwise you will have rapid transitions and the atom should collapse. So to avoid this, what he said was that all the negative energies are completely filled up. By Pauli exclusion principle, an electron cannot go into that, an electron cannot go and fill up that already filled up system state. So you cannot have a transition into that particular state, so they are all filled up. Now this is called the Dirac sea, okay. Now what happens is that there are some interesting physics which happens. Now incidentally, if there is a situation in which a photon is radiated into the Dirac sea, for example, onto the Dirac sea, and a photon has a sufficient energy such that it kicks out one of the electrons which has negative energy, and it pushes into a positive energy state. So it should have minimum energy of 2 mc square, because the energy difference between the two states is mc square minus of minus mc square, that is 2 mc square, okay. So the energy between two systems, so we can push to 1 mc square state, so it pushes up to here essentially, say for example. So it pushes up to here, and then so it becomes a positive energy state, and we wrote the process as this particular case essentially, that so gamma plus a negative energy state, okay, negative energy electron becomes a positive energy electron. But then what happens to the place left over in the vacuum, which is empty? This place left over in the vacuum will be equivalent to adding a positive energy state to the system essentially, because the total vacuum charge is say q time some n times, it is all filled up essentially. And this state is called a hole state, which is vacated by an electron, essentially negative energy electron, and this hole state will appear like a positive energy state, with positive energy, positive charge, okay, because we are always looking at the differences essentially, we always are looking at differences. So this will appear, okay, as a positive, it is like adding to the system, okay, to the vacuum system, to the total system, a positive energy state with a positive charge essentially, because the total charge of the vacuum is essentially conserved, say let us say that it is all fixed essentially, but there is one negative electron charge missing essentially. So this is equivalent to adding, because it is in a negative state essentially, this is equivalent to adding one positive state essentially. So this is equivalent to adding one positive charge. So this is equivalent to the adding to a one positive charge, because what is observable is the difference between the total charge of the vacuum to the observable charge essentially. So, it is equivalent to the. So, if you remove something in the vacuum, it is like creating a particle, it is like creating a particle, okay. It is like creating a particle which is with a positive charge and a positive energy if you do something, okay. So, for the first time I am introducing this nomenclature which is creation. If you remove something in a vacuum and which we can show it explicitly later on in a field theory language, and when we also will do this electromagnetic radiation theory essentially. This is like creating a particle with positive energy, okay, and a positive charge essentially, with a positive charge, and this state is something called as a positron state. Now, if we want to distinguish the positron state with negative energy state essentially, negative energy electron, the negative energy electron has minus E and positron has positive charge and it has positive energy and it has negative momentum of opposite of the negative energy electron essentially, and it also has a spin opposite and the same helicity charge. I will introduce these operators spin operator and the helicity operator have not been introduced, and the velocity operator also has not been introduced, but anyway this just to show the differences between the negative energy state and the positive energy state and the positron which has a positive energy essentially. Again this is called so called the Dirac sea, because of these features is called as the precursor to quantum field theory. Which inherently has many features like many body physics, of many body physics, particle creation and annihilation, and so this Dirac sea introduces all these features which will set up the course for the entire quantum field theory, and in many cases it is equivalent to a quantum field theory. Is but except in some cases it has many body physics, it has particle creation, it has particle annihilation and all the features which are associated with quantum field theory, and that is the reason why it is the Dirac sea has an interesting features. Now, let us go through this process just because we introduced these things essentially. I just wanted to go through this process. Now, so the entire point is that removing a point, the reason why we people say this is removing a negative energy electron from the Dirac sea is equivalent to adding a positive energy, positively charged particle into the theory with equal mass and spin. Okay, with the same mass and same spin. This is important. At that time essentially people had some confusion, but it has been thoroughly shown that the electron will have, the positron has the same mass and the same spin as the electron essentially. Now this is obvious for us because when we are learning modern way the Dirac equations, essentially what we saw was that the u and v wave functions will have the same mass and the same the antiparticle wave functions, okay, have the same mass as we have seen the projection operators and everything. They have the same, the Dirac equation predicts the same mass. In fact, the Dirac equation predicts the same mass and the same spin for the antiparticle and the particle essentially. So with this we are now ready to define the antiparticle as a physical particle which is physical essentially. Like I mentioned, this has been experimentally proven the existence of an antiparticle because it has at the moment after Dirac's theory, I think Pauli wrote a critic complaining that the Dirac theory does not really work, it produces pair creation and pair annihilation and it has all these catastrophes and everything. But around the same time before the Pauli's criticism was published essentially, and it should not be taken seriously, I think Pauli was saying all these things, and before this article could be around the same time Anderson discovered the positron essentially with the same mass and the same spin as the electron. So with this now we can define the antiparticle as a particle with the same mass and same spin, but with all quantum numbers reversed. So these quantum numbers are like it is a spin half particle with the same mass essentially, but quantum numbers reversed means essentially if you have lepton number, baryon number, or if you have say electric charge, okay, all these quantum numbers are reversed. So when I mean electric charge, anything which are charges essentially, okay, mostly what I mean here quantum numbers is charges, all the charges reversed essentially. Now as we have seen that the particle and antiparticle wave functions are related in the Dirac equation. So the u1 can be under some transformation and the first component of the particle wave function is related to the second part of the antiparticle wave function, the v. We have seen these relations already essentially, but what we are trying to do right now is give a physical interpretation for this antiparticle wave functions and give them, tell them that they are solidly. So we have seen this relation, say for example with momentum reversed, with just the momentum reverse, this makes an important thing that this is equivalent to saying that this is one of the indications we will write in, and this is one of the indications saying that for the statement I made saying that the particle and the antiparticle is nothing but particle travelling reverse in time essentially, a particle reverse in time. This will be put up, this is the Stuckelberg-Feynman interpretation of the antiparticle solutions in a quantum field theory setting, but this sort of sets you already into that, this wave function recognition already sets you into that particular picture. That is called the Stuckelberg-Feynman interpretation, which we will mention. time direction reversed. Okay. So good. So this now let's, I mentioned that the Dirac theory is almost equivalent to almost equivalent to okay, almost equivalent to a quantum field theory. Now why does it say so? So because it, we saw one process it could lead to, essentially if the energy of the positron is positive and the energy of the electron is also this process, it's called a pair annihilation process, it's also recognized. The reverse process is called pair creation. A photon, okay, a photon, the reverse process is called pair creation, electron positron. So in which the photon goes into E minus and E plus, both with positive energies essentially. Okay. Now this is not a physical process. In this case the photon is not completely real, it's not it's a virtual photon. So let me just put it like this essentially. So but with this we can create imagine process as follows essentially, pair creation, and now in a fully relativistic theory, so you can have pair creation and pair annihilation. Say for example, so these are process in electron positron pair comes and creates an electron positron pair. Okay. This photon is sort of, it's called a virtual photon for the present essentially. So electron positron exchanges a photon and it creates a virtual pair. In the, I will come to virtual particles in a second, in a bit later in the class essentially, in the set of lectures. Once we come to the virtual particles we will have. So what we have is the process like, okay, pair annihilation. So and pair creation essentially, these are exactly like quantum field theories. These are exactly like quantum field theories in which you have multiple particles. The particle number is no longer conserved, okay, because the particles can annihilate each other and they can they can annihilate and they can create. So the particle number is no longer conserved, and this leads to completely different physics in a relativistic setting compared to any other in a non-relativistic setting essentially. Okay. Now this has significant implications. The process of pair creation and pair annihilation has significant significant physical effects essentially, what we can physical consequences, and these are all possible for interpretation in terms of a Dirac sea essentially, in terms of a Dirac sea. Okay. Now this is a fully relativistic picture essentially, in a fully relativistic picture. So where the Dirac theory is augmented with an radiation field which is nothing but the electromagnetic radiation field essentially, the EM theory essentially. Now in the presence of this photons, so it can so it is important that you need some interaction. So okay, here we are talking about electromagnetic interaction. So this the process of pair creation and annihilation is important in the presence of some interactions essentially. So in the presence of say for electromagnetic interaction, this happens essentially. So I'll come back to this when we do the full relativistic theory of the Dirac theory, which we will do in the coming sense. But what I will try to do is give you the physical picture right away, and we will see this in the coming lectures, how to do it mathematically essentially, and the full consequences we will see a little bit. One of the first consequences of this thing is that there is something called electric charge renormalization. So for the first time you are hearing the word renormalization, but now but this is also called, in the old days it was called something else essentially, but we do not have to go into that essentially. Now let us think of some process like in classical mechanics or like in classical electromagnetic theory essentially, and now distinguish in a relativistic quantum mechanical picture. Imagine that there is a test electron sitting here essentially, some test set electron sitting here, and then there is another test electron sitting here. Like I said, this is equivalent to a process in which the electron, now we want to measure the charge of this electron essentially. To measure the charge of the electron, because depending upon the distance it is in, or depending upon in a relativistic setting essentially, depending upon the distance, or so that means you need for shorter distances you need more and more energies. Okay, you want to see, as you want to probe closer and closer to the electric charge, you need to give more and more energy to the photon essentially. Suppose if you are measuring the distance at a very far distance at electric charge, you will see some charge, some E essentially, some charge which we call it as E0. Let me call it as some E0. Suppose I want to measure the same electric charge of this particular photon by sending it to some photon from a test charge at some distance here essentially. Some distance here, what happens is, because this energy of this photon should be larger compared to this distance, compared to the distance between this distance essentially. Okay, this energy of the photon, now if you are measuring from this distance, the photon energy will become more and more, because you want to measure the charge of the electron. Now remember, the way you measure the charge of the electron is only through some interaction. So you can only measure it through some interaction, by radiating another photon, by shining a light on it, or by sending one more electron closer to it, or something like that. Now if you keep sending the electron closer and closer, suppose you put the electron here at some distance x0 and the charge is 0. Now if you move the distance to x1, say for example, which is this one, because the distance is okay, because the distance is closer, the radiated electron will the radiated photon also will started becoming more and more energetic essentially, because you are measuring closer to the charge of the electron. Okay, so very close to the where the electron is sitting essentially. Okay, say if it is sitting at a point x0, say for example, you are bringing closer and closer essentially, y0 say for example. So what does this photon do? At some point what does that do is that it will start creating electron positron pairs essentially. It starts creating electron positron pairs. So what you have is the electron is surrounds itself, the bare electron surrounds itself by creating of virtual positron electron pairs essentially. These are all virtual, these are all, it's like a cloud essentially. This cloud surrounds itself around this essentially, and then what we are seeing is the sum of this entire charge essentially. You are seeing the sum of this entire charge as the electric charge E0. So, as you go closer you will measure its charge which is E1. Now, if you put in even further, much closer, another thing at a distance x2, this photon charge will be this photon energy which will be even larger, and the number of electron positron pairs is even larger. So, as you are probing closer and closer, as you are probing the electric charge closer and closer, you are probing this huge cloud of this electron positron virtual pairs, which are all like an dielectrical effect essentially. So, which are all encompassing, all the positive charges are clouding this negative energy charge essentially of the electron. Okay, they are all clouding this negative energy start of the electron. So, what you see at a very large distance, slightly say imagine that at a distance of atomic energy, atomic distances around 1 Fermi or something, you start electric charge to be around, okay. So, 1 Fermi, or so you see the electric charge to be so and so. So, around 1 by 137 atomic distances or something essentially. Okay. Even larger, 1 atom Armstrong, say let us say. Okay, 1 by 137, that is nothing but E square by 4 pi, your fine structure constant essentially, E square by 4 pi. Okay, or rather let me write it in terms of 4 pi by square root of 4 pi by 137. Now, as you move closer, as you start moving closer and closer, okay. So, suppose at distance of around 1 Fermi and even smaller, this electric charge E1 becomes 4 pi by 127. So, the electric charge keep increasing. So, what you are seeing at much larger distances, is clouded by this entire creation of this virtual electron positron pairs essentially. But once we start probing deeper and deeper, you start seeing the electric charge which is called the bare charge. The bare charge, which is a consequence of this creation of this virtual electron positron pairs. And as you will see, if you measure the charge with respect to the distance, it will you start seeing the charge, and if you measure the charge with respect to the distance at large distances, the charge is very very small. Okay. At very very small distances it becomes infinity essentially, it becomes infinity. Charge distance. Okay. As distance tends to 0, it just falls off essentially, it just falls. Maybe my plot is not explicit, it should be logarithmic, and this effect can be calculated in theory. Okay. This effect can be calculated in theory, and this effect is logarithmic. This plot is a logarithmic plot essentially. So, this effect is logarithmic, the charge changes logarithmically with reference to distance, or instead of distance in relativistic theory you can replace it with energy essentially, energy or momentum or energy q square, we will come to that essentially, energy. So, this entire process is called charge renormalization, and this is purely because of the creation of virtual electron positron pairs, which we have discussed as due to the presence of the virtual electron which is a consequence of understanding of the Dirac sea essentially, which is a consequence of the understanding of the Dirac sea. Okay. And it is a consequence of pair creation and pair annihilation, which we know are a consequence of the Dirac sea essentially and the Dirac theory. So, the Dirac theory has very important consequences. This gives you all the features associated with the full quantum theory results essentially, and the Dirac hole theory is a very important step towards understanding of our nature in the relativistic quantum mechanical system essentially. So, we will stop here, okay, and then we will continue. I will come back to Dirac sea a bit later essentially, maybe in a couple of more lectures essentially when we start doing in the electromagnetic theory. Okay. But for now this gives you the features of the Dirac sea. So, in the next class we will continue with various other operators and other solutions of the Dirac equation essentially, like the Weyl solutions and the Marano solutions and so on. So, and then we will move to the electromagnetic Lagrangian of the Dirac Hamiltonian essentially. Okay. I will stop here. Thank you very much.